The Dark Universe, Dark Matter, Dark Energy, and Our Cosmic Fate. Prologue, Gazing into the Dark. When we look up at the night sky, the stars glimmer back at us in familiar constellations, yet what we see is just the tip of the cosmic iceberg. Modern astronomy has revealed that the vast majority of the universe is invisible. Only about 15% of the matter is the normal atoms we know. Everything else is dark matter, an unseen substance holding galaxies together. Even more mysterious is dark energy, an unknown component making up roughly 68 to 70% of the universe's total energy and driving the cosmos apart. These dark forces govern the destiny of the cosmos, yet they reveal themselves only through their gravitational footprints and the history of expansion. In this film, we will journey from the first moments after the Big Bang through the grand architecture of the cosmic web, following clues from the microwave afterglow to the explosions of distant supernovae. Along the way, we will hear from the great voices of science, from Carl Sagan's poetic reflections on star stuff to Katie Mack's bold explorations of the end of everything, as we strive to bring light to the dark universe. The Big Bang, a universe is born. In the beginning was the Big Bang, a cosmic dawn that set the stage for everything we see today. A fraction of a second after the Big Bang, the universe underwent a blistering burst of growth known as inflation. During inflation, space itself expanded far faster than the speed of light, smoothing out any initial wrinkles in geometry and magnifying quantum fluctuations into the seeds of galaxies. This extreme expansion laid the groundwork for the cosmic tapestry that would follow. When inflation ended, its energy converted into matter and radiation, the true Big Bang in earnest. The infant universe was so hot and dense that for a brief moment it was opaque and uniform. Figure: NASA visualization of cosmic inflation and expansion over 13.8 billion years. In that first second, the universe was an incandescent plasma of particles and light. As the fireball cooled in the first few minutes, nucleosynthesis forged the first atomic nuclei. Hydrogen and helium nuclei fused from protons and neutrons, with trace amounts of deuterium and lithium appearing as the blast wave expanded and cooled. By about 5 minutes after the Big Bang, helium nuclei were locked in, and the cosmos was still too hot for electrons to remain bound to nuclei. The result was a hot, glowing fog of charged particles and photons. Listening to the afterglow, cosmic microwave background. Roughly 380,000 years after the Big Bang, the universe had cooled to about 3,000 K. Electrons and nuclei finally combined into neutral atoms and the fog lifted. Suddenly, light streamed freely through space. This recombination era left a glow that still pervades the sky, the cosmic microwave background. It's the oldest light we can see, the afterglow of creation. In the late 1940s, theorists like Gamow, Alpher, and Herman predicted this relic radiation should exist. In 1964, radio astronomers Arno Penzias and Robert Wilson accidentally detected a persistent hiss in a Bell Labs antenna, a uniform 3.5 K microwave glow from every direction. This discovery of the CMB provided stunning confirmation of the hot Big Bang model. Today, that ancient light has cooled to just 2.73 K, but it carries a rich pattern of tiny ripples. NASA's COBE satellite, launched 1989, made the first full-sky map of the CMB and showed it had a nearly perfect blackbody spectrum at 2.73 K. COBE also detected very faint anisotropies, temperature variations at the level of 1 part in 100,000. These minute ripples were the primordial seeds. The successor missions WMAP, launched 2001, and Planck, launched 2009, mapped the CMB with ever greater precision. The pattern of hot and cold spots in the CMB tells us the size, composition, and age of the universe. Remarkably, it confirms that the early universe had tiny fluctuations, consistent with inflationary predictions, which then grew under gravity into the galaxies and clusters we see today. Shadows in the Cosmos, the mystery of dark matter. As telescopes probed the universe in the 20th century, a deep mystery emerged. Galaxies and clusters moved as if there were far more mass than their visible stars and gas could account for. In 1933, Swiss astronomer Fritz Zwicky studied the Coma galaxy cluster and found its galaxies were moving so fast they should have flown apart unless there was huge unseen mass providing extra gravity. He proposed dunkle materia, dark matter, to explain the missing mass. Decades later, in the 1970s, Vera Rubin and Kent Ford measured the rotation curves of spiral galaxies and found the same puzzle. Stars in the outskirts of galaxies were orbiting far too quickly to be held by the gravity of the visible stars alone. The conclusion was unavoidable. Galaxies and clusters contain far more mass than we can see. Dark matter doesn't emit or absorb light, so it cannot be observed directly with telescopes. Instead, astronomers infer its presence through gravity. One key tool is gravitational lensing. Einstein's theory of general relativity tells us that mass warps space, bending the paths of light. A massive galaxy cluster can act like a giant lens, distorting and magnifying the images of background galaxies. The Hubble Space Telescope has captured spectacular lensing clusters, where background galaxies appear as stretched arcs around a cluster's center. By carefully modeling these distortions, astronomers can map the distribution of mass, both visible and dark, in the lensing cluster. For example, observations of the cluster Abell 2813 show golden arcs from background galaxies bent by the cluster's gravity, allowing scientists to infer that most of the mass is an unseen component. Figure: a Hubble Space Telescope image of galaxy cluster Abell 2813 demonstrating strong gravitational lensing. Background galaxies appear as long, curved arcs magnified by the cluster's mass. Lensing has even provided dramatic proof of dark matter's existence. In the famous Bullet Cluster collision, two clusters of galaxies have recently passed through each other. X-ray images, pink, show the hot gas, the majority of normal matter, slowed by the collision, while gravitational maps, blue, show most of the mass has passed through unimpeded. This separation of dark and normal matter is often described as a cosmic smoking gun for dark matter. Simulating the cosmic web, the role of dark matter. Computer simulations have revealed how dark matter sculpts the large-scale structure of the cosmos. In the early universe, the tiny ripples seen in the CMB gradually grew over billions of years. Dark matter clumped under gravity to form an intricate cosmic web, vast filaments and sheets of invisible matter stretching across space, with galaxies tracing the luminous knots. Simulations such as Illustris and others produce images of this web, showing dark matter filaments connecting clusters and voids. Figure: simulation of the large-scale cosmic web, showing dark matter filaments blue connecting brighter clusters of matter. The image above from NASA Hubble Science illustrates this hidden network. As scientists note, a smooth early universe with tiny density variations evolved into a web of filaments and sheets made primarily of dark matter. Hubble's deep surveys have even begun to map this web in 3 dimensions. An international team used 575 overlapping Hubble images to create the first 3D map of dark matter filaments stretching into the distance. The result confirmed the theory. The dark matter network is collapsing at the intersections, growing clumpier over time. Searching for the invisible, dark matter candidates. If dark matter dominates the universe's mass, what is it? Particle physicists have proposed new, undiscovered particles that could fill the bill. These particles would interact only weakly with normal matter and light. 2 leading candidates have emerged: WIMPs, weakly interacting massive particles, and axions. An axion would be extremely light, 1 billion times lighter than an electron, and very elusive. Both are purely hypothetical so far. To search for WIMPs, huge detectors are buried deep underground to shield them from cosmic rays.
These experiments used tons of ultra-pure liquid xenon or other targets, hoping to catch the rare moment when a WIMP collides with a nucleus. Recent results from the Lux-Zeppelin experiment, for example, set the world's best limits. After hundreds of days of running, Zeppelin found no WIMP signals in the mass ranges it probed, ruling out many predictions. In fact, Zeppelin is so sensitive it has even begun detecting neutrinos from the Sun, entering the so-called neutrino fog. Each null result narrows the parameter space, but the dark matter still hides. Axion hunters try very different methods. For example, they use strong magnetic fields to convert dark matter axions into photons. Experiments like ADMX and planned ones like MADMAX are targeting the range of masses favored by theory. So far, none of these experiments has made a definitive discovery. In the end, as the Department of Energy puts it, dark matter has only been seen by its gravity, like footprints on a beach.
The universe is not what it seems. Dark matter and dark energy. Look up at the night sky, and you might feel you are seeing everything there is. Stars glitter across the darkness, galaxies stretch into the distance, and the universe appears vast but understandable. Yet this impression is deeply misleading. What we see is only a thin surface layer of reality. The universe, it turns out, is dominated by forces and substances we cannot see, touch, or directly detect. The cosmos is not what it seems. Modern astronomy has revealed a startling truth. All the stars, planets, gas clouds, galaxies, and life itself are made from just a tiny fraction of what exists. Ordinary matter, the atoms that make up everything familiar, accounts for only about 5% of the universe. The remaining 95% is hidden in two mysterious forms, known as dark matter and dark energy. Together, they control the structure, evolution, and ultimate fate of the cosmos. This realization represents one of the greatest paradigm shifts in human history. For most of our past, humans believed the universe was composed solely of visible objects. Ancient civilizations mapped the stars and planets, believing the heavens were orderly and complete. Even after the scientific revolution, when Copernicus displaced Earth from the center and Newton explained gravity, the universe still seemed made of tangible, measurable things. That picture began to crack in the 20th century. Einstein's theory of general relativity revealed that space and time are not rigid backdrops, but flexible and dynamic. Space can stretch, bend, and ripple. Soon after, astronomers discovered that the universe is expanding. Galaxies are moving away from one another as space itself grows. The discovery of the cosmic microwave background confirmed that the universe began in a hot, dense state nearly 14 billion years ago. This ancient radiation, still detectable today, serves as a fossil imprint of the early cosmos. By studying its subtle patterns, scientists learned something astonishing. The universe contained far more gravity than visible matter could provide. The first clues came from galaxy clusters. When astronomers measured how fast galaxies moved within clusters, they found they were traveling too quickly to be held together by visible mass alone. According to known physics, the clusters should have flown apart. The only solution was that large amounts of unseen mass were present, exerting gravitational pull. Later, similar anomalies appeared inside individual galaxies. Stars at the edges of spiral galaxies orbit far faster than expected. Instead of slowing down with distance from the center, their speeds remain nearly constant. This flat rotation pattern implies that galaxies are embedded within enormous halos of invisible matter, extending far beyond their visible boundaries. This unseen substance was given a simple name: dark matter. It does not emit light, absorb light, or reflect light. It does not interact with ordinary matter except through gravity. Yet it outweighs normal matter by more than 5 to 1 and provides the gravitational backbone of the universe. Without dark matter, galaxies would never have formed. In the early universe, ordinary matter alone was too smooth and too diffuse to clump into stars and galaxies. Dark matter collapsed first, forming gravitational wells that pulled gas inward. Stars ignited, galaxies took shape. In this sense, dark matter is the cosmic scaffolding upon which the visible universe is built. The large-scale structure of the cosmos reveals this hidden architecture. Galaxies are arranged along vast filaments stretching hundreds of millions of light-years, separated by enormous voids. This cosmic web traces the distribution of dark matter. Ordinary matter simply follows its gravitational blueprint. Gravitational lensing offers another window into the invisible. Massive objects warp spacetime, bending light that passes nearby. By observing how distant galaxies appear distorted, astronomers can map mass even when it is completely unseen. These maps consistently reveal vast concentrations of dark matter where little or no visible matter exists. One dramatic example involves galaxy cluster collisions. When clusters crash together, their ordinary matter, mostly hot gas, slows down and heats up. Dark matter, however, passes through almost unaffected. Observations show the gravitational mass separating from the visible gas, offering direct evidence that dark matter is real, distinct, and largely collisionless. Yet dark matter, strange as it is, accounts for only part of the mystery. In the late 1990s, astronomers studying distant exploding stars made a discovery even more shocking. By measuring how bright these supernovae appeared, scientists could determine how fast the universe was expanding in the past. They expected to find that expansion was slowing due to gravity. Instead, they found the opposite. The expansion of the universe is accelerating. Something is pushing galaxies apart, overcoming gravity on the largest scales. This unknown influence was named dark energy. Unlike dark matter, which pulls things together, dark energy drives space itself to expand faster over time. Dark energy appears to be a property of space rather than matter. As space expands, more dark energy comes into existence, strengthening its effect. Today, it accounts for nearly 70% of the universe's total energy content and dominates cosmic evolution. The simplest explanation is that empty space has energy, an intrinsic energy of the vacuum itself. Einstein's equations allow for such a term, known as the cosmological constant. Ironically, Einstein once introduced it to prevent the universe from collapsing, then later rejected it. Now it may be essential after all. But dark energy remains deeply mysterious. Calculations from quantum physics predict vacuum energy values vastly larger than what we observe. Something appears to cancel or suppress it, but no one knows how. Other theories propose that dark energy changes over time or arises from new fields permeating space. Some even suggest gravity itself may behave differently on cosmic scales. Despite decades of effort, neither dark matter nor dark energy have been directly detected. We infer their existence only through their gravitational effects. This makes them among the most profound unknowns in science. Yet we are living in a remarkable era. New telescopes and surveys are mapping billions of galaxies, tracing the growth of cosmic structure and measuring expansion with unprecedented precision. Future missions aim to determine whether dark energy is constant or evolving, and to uncover the true nature of dark matter. Each observation brings us closer to understanding a universe that is far stranger than imagined. The visible cosmos, the stars, planets, and galaxies, is only the luminous foam atop a vast, dark ocean. We are made of the rarest substance in existence, living in a universe dominated by the unseen. Yet from this small island of light, we have learned to read the universe's deepest signals.
we have discovered that reality extends far beyond appearances, that the cosmos hides its greatest truths in darkness. The universe is not what it seems, but in seeking to understand it, we reveal something equally remarkable: the human capacity to question, to imagine, and to explore even the invisible. The greatest journey is not outward into space, but inward towards understanding.
Black holes explained, from theory to reality. In the depths of the cosmos lies one of the most extreme and fascinating objects ever imagined. Black holes are invisible by nature, yet they shape galaxies, bend light, distort time, and challenge the very foundations of physics. Once dismissed as mathematical curiosities, black holes are now known to be real, abundant, and essential to the structure of the universe. This is the story of how an abstract idea born from equations became one of the most powerful realities in the cosmos. At the beginning of the 20th century, gravity was thought to be a simple force acting across space. That understanding changed forever in 1915 when Albert Einstein introduced his theory of general relativity. In this new vision, gravity was no longer a force pulling objects together. Instead, mass and energy warped the fabric of space-time itself. Objects moved not because they were pulled, but because space-time curved beneath them. Hidden within Einstein's equations was a startling possibility. Under extreme conditions, space-time could collapse entirely, forming a region from which nothing could escape. Soon after, physicists realized that if enough mass were compressed into a small enough volume, gravity would overwhelm all other forces. Space would curve inward endlessly, and time would effectively come to a halt. At first, even Einstein doubted that such objects could exist in nature. The idea of matter collapsing without limit seemed unphysical, almost absurd. But the universe had other plans. As astronomers studied the lives of stars, they discovered that the most massive stars end their lives in violent explosions, known as supernovae. When nuclear fuel is exhausted, the outward pressure that supports a star disappears. Gravity takes over, crushing the core inward. For stars several times more massive than the Sun, not even the pressure of neutrons can stop the collapse. The result is a black hole, a region of space-time so warped that escape becomes impossible. Surrounding every black hole is an invisible boundary known as the event horizon. This is not a physical surface, but a mathematical threshold. Once crossed, all possible paths through space-time lead inward. Light, the fastest thing in the universe, cannot escape. To an outside observer, time appears to slow down at the horizon. To anything falling in, the journey continues inexorably toward the center. At the heart of a black hole lies the singularity, a point where density becomes infinite and the known laws of physics break down. Here, our equations fail. Space and time lose their meaning. The singularity represents the edge of human understanding. Black holes come in different sizes, but all share the same fundamental nature. The smallest are stellar mass black holes, formed from the collapse of massive stars. They contain several times the mass of the Sun, compressed into a region no larger than a city. Hundreds of these have been detected in our galaxy alone, often revealed by their interactions with companion stars. Larger still are intermediate mass black holes, thought to form through repeated mergers or the collapse of dense star clusters. For decades, they remained hypothetical. Only recently have observations begun to reveal convincing candidates, bridging the gap between stellar and supermassive black holes. At the top of the scale are supermassive black holes,
monsters containing millions or even billions of times the mass of the Sun. These giants reside at the centers of nearly all galaxies, including our own Milky Way. They influence the motion of stars, regulate galaxy growth, and shape the cosmic environment on the largest scales. Despite their name, black holes are not cosmic vacuum cleaners. Objects must come very close to be captured. In fact, if our Sun were replaced by a black hole of the same mass, the planets would continue orbiting almost exactly as they do now. The danger lies not in their pull, but in their proximity. Black holes reveal themselves not by what they emit, but by what they affect. As gas and dust spiral toward a black hole, they form an accretion disk, heating up to extreme temperatures. This glowing matter emits powerful radiation, especially in X-rays. In some cases, black holes launch colossal jets of particles at near light speed, stretching thousands of light years into space. In our own galaxy, stars near the center move at incredible speeds, tracing tight orbits around an unseen object. The only explanation is a supermassive black hole with millions of times the Sun's mass, confined to a region no larger than our solar system. In recent years, humanity has learned to detect black holes in a new way, by listening to the universe itself. When two black holes spiral together and merge, they shake space-time, sending ripples outward at the speed of light. These gravitational waves were predicted by Einstein a century ago, and finally detected in 2015. Since then, dozens of black hole mergers have been observed, revealing populations of black holes across the universe and confirming that space-time is dynamic and responsive. Perhaps the most iconic breakthrough came when humanity captured the first direct image of a black hole. By linking radio telescopes across the globe, scientists formed an Earth-sized virtual telescope capable of resolving the event horizon of a supermassive black hole in a distant galaxy. The image revealed a glowing ring of matter surrounding a dark shadow, exactly as predicted by general relativity. Later, a similar image was captured of the black hole at the center of our own galaxy. For the first time, black holes moved from abstract theory to visual reality. Yet, black holes are not merely cosmic destroyers. They are also laboratories for new physics. In the 1970s, Stephen Hawking made a shocking discovery. By combining quantum mechanics with relativity, he showed that black holes are not completely black. Quantum effects near the event horizon allow a faint trickle of radiation to escape. Over immense timescales, this Hawking radiation causes black holes to slowly evaporate. This insight revealed that black holes have temperature, entropy, and obey the laws of thermodynamics. It also introduced one of the deepest puzzles in modern physics, the information paradox. If black holes eventually evaporate, what happens to the information about everything they swallowed? Quantum theory says information cannot be destroyed. Relativity seems to say it is lost forever behind the horizon. Resolving this contradiction has driven decades of research into quantum gravity, holography, and the nature of space-time itself. Some theories suggest that information is encoded on the event horizon, smeared across its surface like data on a cosmic screen. Others propose that information escapes gradually through subtle correlations in Hawking radiation. While no consensus exists, progress continues to reshape our understanding of reality. Black holes have also inspired speculation that stretches the imagination. Some solutions to Einstein's equations allow for wormholes, tunnels connecting distant regions of space-time. Others predict white holes, hypothetical opposites of black holes that expel matter rather than absorb it. A few radical ideas suggest that black holes could give birth to new universes, with our own Big Bang emerging from a similar process in another cosmos. While these ideas remain speculative, they underscore an essential truth. Black holes sit at the frontier of knowledge, where certainty gives way to possibility.